Our last topic for the class is another geometry problem. And this is going to deal with the convex hull algorithm. And in particular, we're going to go through one called a gram scan. And it's an interesting algorithm. That's one of the reasons I'm going to go over it. It's pretty easy to understand. It's pretty easy to implement. And we'll see how it works. Now, first of all, I need to describe what a convex hull is. It's actually a really useful property. There's a lot of cases where convex hull is needed for geometric calculations. But the way that I like to think about it is if you imagine a pegboard with a bunch of points, and the points are tacks that are stuck into the board, the push pins that kind of stick up. And if I were to wrap some rubber band around all of the points, and then I were to let the rubber band go, it would end up forming the convex hull of that set of points. It's basically the set of points that rubber band would encounter as it gets as tight as it can. And notice there's going to be some points that are inside. There's some points that are inside of the convex hull that they don't affect it. They're not a part of the hull itself. There's other points that are some of the given points that will form the convex hull. And basically, when you say I need the convex hull, you're asking for the set of points that form that boundary. Now, you can think of this as something like, okay, these are, I need fencing, and I need the minimum fence that's going to enclose my property or the important things on my property, and these points are the important points on my property. That's an example of the type of thing that you would use a convex hull for. It's also the way that you generally determine is something, do I need to respond to it? Is it like within my region? And anyway, there's a whole variety of uses for this idea. Now, there's several algorithms that will form the convex hull. The gram scan is, to me, a pretty nice one because it's kind of easy to understand, and it really builds up on everything that we have so far. So the key thing that we need for the gram scan is you need to have the left or right turn function, and we talked about this in the earlier discussion about geometry problems and building up a geometry library. But just to remind you, the idea here is if I'm given 3 points A, B, and C, the idea is as I go from A to B to C, am I turning left or am I going to the right? Okay, so those are the two options. Is do I go left or do I go right? And if you remember, the way that you actually compute that is you form two vectors, A to B, B to C, or you can form A to B, A to C. Either one of those is fine. And I take the cross product between them. And if the cross product is positive, it's turning to the left. If the cross product is negative, it's turning to the right. Okay, so that basic functionality, left or right turn, that is the thing that we are going to use in the gram scan. So if you've built up a library of geometry calculations, then that should be part of it. You should be able to take in 3 points, A, B, and C, and determine as you go from A to B to C, are you turning left or are you turning right? Okay, so the gram scan algorithm, the first thing that you want to do is you want to find an extreme point. If you actually look at the convex hull, you can kind of picture it in your head. Any extreme point, if I pick any direction, if I take the extreme point in that direction, so the extreme point in this direction might be this point right here, that point is going to lie on the convex hull. Okay, and so the one that you typically use is you find the minimum y value. Okay, so I'm going to find the minimum y value is going to be the extreme point that I care about. And if there's a tie, then I will take the min x from among those. So remember that for geometry problems, you need to be careful about things like ties. You need to make sure that you handle all of that. It's important to always handle those special cases. It's not like there's just a single minimum y value. So if I'm given a bunch of points in space, Okay, I want to find the minimum y value, and it looks like this one here is probably the minimum. So that would be the point that I have. That's going to be the one that I start from. If I have more than one point along the same value, then I would pick the smallest x value among those points. Okay. Then the next thing we are going to do is we are going to order them by counterclockwise angle. Okay, in other words, if I take a vector, say that this was my point right here, if I form a vector to each of these other points, I want those vectors to be organized in counterclockwise order from one to another. Okay, and then what I'm going to do is I'm going to repeat this process over and over, where I will go from one point and I will add the next point. So this is going to be the process that repeats. To the convex hull, and if it is a left turn from the previous, then I just continue. However, if it is a right turn, from the previous, then I will remove the previous one. Okay, and I'm going to repeat that over and over. So as many times as there's a right-hand turn, I'll remove it. So the easiest way to see this by far is just to run through an illustration of it. So I'm going to generate a bunch of points. I'm going to try to do this kind of at random here. I don't know. I haven't predetermined these, so I hope this one works well. So I'm going to order these points by angle. And a couple of them I'm having to show you what the angle is because I drew them a little too close together, but hopefully you'll get the idea. Okay, and I find the lowest, first of all, I found the lowest value, so I'm going to use green for the points on the convex hull. So that point is green. That's my lowest y value. I know it's on the convex hull. And now I'm going to add points in order. So I'll add the first point. If you think about that, that one's always going to also be an extreme point. Okay, so I find that first point along the way. And then I'm going to keep adding another point. As long as it is a left-hand turn, I keep it. So I add the next one. It's that point right there. Notice that as I go from here to here to here, that is a left-hand turn. And so I keep that point. Okay, I go to the next point. It's that one right there. That is another left-hand turn. So notice that as I went from here to there, I had to turn left. And so I keep that point. So I add that in. Now I add the next point. Now you'll notice something though. I'm going from here to here to here. That is a right-hand turn. And so what I'm going to do is I'm going to remove the previous point. I'm going to remove that point. This one goes away, so it's not there. And now what I'm left with is those vectors. And if I look at these vectors, as I go from here to here to here, that is now a left-hand turn. That's okay. So I'm going to keep that point, and I'll keep that point, and I'll keep the previous one. I add my next point in. That's this one here. It is a left-hand turn. As I went from there to there, that was a left-hand turn, so I keep it. I add the next point in. Now notice that as I go there, guess what? It's a right-hand turn again. I've got to get rid of this. And so now I'm looking for that particular turn. And that particular turn is now a left-hand turn. I add the next one in. It's still a left. There's a left, and so on. And so at this point, I have found my convex hull. It's these points that it's not the two red in X. Those are interior points. All the rest of the points are on the convex hull. Now, there are going to be times, and I'll see if I can do one very quickly that I generate on purpose this way. I can have points where I might seem to create things that are on the convex hull, and then I have something else that's going to make me have to undo several of them. So imagine that these black points are there. So I've got this edge, that one, that one, that one, and that one. Okay, and actually just to make it clearer, I'll put this one out here. Okay, and so notice that what I would do is I'd start with this point, I'd start with that point, I would add that one, I would add that one, I would add that one. Everything seems good so far. But now when I add this one, I look and this was a right-hand turn. So I get rid of that. And now I look from here to here to here. Well, guess what? That's also a right-hand turn. So I get rid of that. And so now I look from here to here to here. Again, a right-hand turn. So I get rid of that. And now I have a left-hand turn, everything's good. And so I end up with just these 3 points on the outside as my convex hull. Okay, that is the gram scan algorithm. It is something that you should be able to implement. It's not particularly tricky. You just basically keep your stack of what your points are, and you always look 2 levels back on the, or 2 points back on the stack, and sometimes you get rid of one of the things in between. You get rid of the one before you, and just keep your list as you go along, and it's there. Just when I talk about a stack, just so you can see these, if this is point 0, 1, 2, 3, 4, 5, the way this would be built up is I know 0 is there, I know 1 is there, I add 2, we're good, 3, we're good, I add 4, we're good. When I try to add 5, I then say, nope, it doesn't work with 4, and then I look at 2, 3, 5, nope, that didn't work either. I now look at 1, 2, 5, nope, that didn't work either. I now look at 0, 1, 5, well, that does work, and that's what I end up keeping. Okay. So that's the gram scan algorithm. Just so you know, convex hull, there are some totally different ways of doing it. You know, one of them where you sort of find 2 subsets and you form the convex hull of each one, and then you merge those 2 convex hulls together, sort of this merge sort idea. There's a couple of others that are out there. There are some 3D algorithms. This gets much more complicated in 3D, identifying what the points are on the convex hull. There's things called a gift wrapping algorithm. So the idea of the gift wrapping algorithm in 2D, it's a little bit easier to see. You just sort of go to an extreme, and then you find the next one, and the next one, and the next one, and the next one, and the next one. And you can imagine every time you're sort of looking through all the other points to find what's the smallest angle of all of the remaining points along the way. So you're just sort of wrapping around the outside. But gram scan works well. It's a pretty efficient algorithm. You end up only visiting each node a few times, you know, generally just once, or a linear number of times, once to add it and possibly once to take it away. Okay. That's the convex hull algorithm. Hopefully it's something that you can all implement if you run across that problem, and something you can work with.